Hello, class. In this activity, we begin with the introductions to logarithms. In a previous activity, we talked about a problem where we tried to model the number of cell phones in any given year. And I believe our base year was 1996. And at some point, we asked, how long will it take for the number of cell phones to double? So the initial value of cell phones, I believe, was 44 million and change. So double 44 would be 88 million. And the way we solved this problem back then was we graphed both sides of the equal sign, right? So we had y1 would be the left side of the equal sign, y2 would be the 88 million, and the intersection would be our answer, right? That would tell us how long it took. With logarithms, we could actually solve this without graphing, okay? But before we get into the steps to solve this problem using logarithms, we should begin with some of the basics. So if you look at example 1, it says solve for x. Okay, so if I had 2 raised to the x equals 8, I'm really asking what value of x makes this statement true. So if on the right side I have 8, that means I'd have to raise 2 to some number that would give me 8. So the answer would be x equals 3, right? Because 2 times 2 times 2, or 2 cubed, would give me 8. So when I look at a practice problem, 5 raised to the x equals 25, what value of x would make this true? Well, the answer would have to be x equals 2. Right, so x equals 2 is our answer because 5 raised to the 2 equals 25. If I look at practice problem number 2, really we're saying what value of t would give me 10,000. So the answer would be t equals 4 because 10 to the 4 gives me 10,000. All right, problem number 3, it's a little tricky, right? We have to think about this. E raised to what number would result in 1 over e? Well, let's think about this. If I had e raised to the 1, that would be e, right? E raised to the 1 results in e. However, I need 1 over e. So I know that e to the negative 1 would result in 1 over e. So I know my answer would be x equals negative 1, right? What value of x here would result in 1 over e? The value of x would be negative 1. So here's my final answer. Oops, not e equals negative 1. It should be x. Excuse me. There we go. X equals negative 1. Okay. So now we begin to discuss logarithms, and they say, well, most exponential equations can't be solved so easily, right? So yeah, 5 to the x, that was easy to solve, or 10 to the t was easy to solve. But what would happen if I gave you 2x equals 7, right? There's no number for x that I could quickly think of that would result in 7. All right, so we're going to have to think about the use of this new operation called the logarithm, okay? And then you can think about, well, what is a logarithm? Well, if you look at this problem, x divided by 4 equals 35, we undo the division by multiplying, right? We would multiply both sides of this equation by 4 to free x, to get x by itself. Or if I was adding x plus 5, I could undo the addition, right? By subtracting, right? I would subtract 5 from both sides to get x by itself, where you'd have x equals 4. So the logarithm undoes the exponent, right? Just like division undid the multiplication here, or I'm sorry, multiplication undoes the division, subtraction undoes the addition, the logarithm frees the exponent, all right, or undoes the exponent. All right, so another way to write 2 to the x equals 7 is x equals log base 2 of 7. Okay, so what happens is we're trying to get x by itself. By introducing this logarithm, you'll notice that now we have x isolated. Right, the point was to get x by itself. So down here, they give us a definition, right? B raised to the p equals t is equivalent to p equals log base b of t. I know that's a mouthful. But the bottom line is, just like we freed the exponent, right, which was x, we got x by itself. Here we freed the p. We end up with p by itself, okay? So when I look at example 2, 5 squared equals 25 is the same as log base 5 of 25 equals 2. So if you think about this, the base of my exponent is 5. The base of my log is 5, okay? The exponent's what we're trying to free, and here's my exponent free. And then the 25 comes inside, okay? And if you look at example 3, the base of my log is 4, so the base of my exponent's going to be 4. Here, 3 is by itself. Oops. Right, the 3 is by itself. And in exponential form, the 3 is your exponent. Okay, so it says, all right, let's practice a few of these. Write each of the following in logarithmic form. So when I look at number 4, okay, the base of my exponent's 2. So remember, it says logarithmic form. I'm going to need the word log somewhere. So there's log. Now the base of my exponent's 2, so the base of my log will be 2. The exponent's what we're trying to get by itself for free. And the 32 comes inside. So we have something that looks like that. Log base 2 of 32 equals 5. All right, let's take a look at number 5. For number 5, the base of my exponent's 3, so I'm going to write log base 3. The exponent's what we're trying to get by itself, and the 81 comes inside. All right, so log base 3 of 81 equals 4 is equivalent to 3 raised to the 4 equals 81. Okay, let's take a look at number 6. Number 6, the base of my exponent is 4, so I write log base 4. The 1024 comes inside, and the 5 is all by itself. Okay. Number 7, all right, so now they have a fraction and a negative number. Well, the steps are still the same. The base of my exponent is 6. The 1 over 6 comes inside, and the negative 1 is on the outside. Okay, so number 7 is done. Number 8, okay, now our exponent's a fraction. Again, the base of our exponent is 16, so I write log base 16. The exponent's the 1/2, and the 4 comes inside. Okay, so this is log base 16 of 4 equals 1/2. Okay, so we'll stop here and we'll continue with problems 9 and 9 through 13 in the next video. Okay?